In the last video, we've created an example PERC cell. So a PERC cell, or a localized BSF cell, is a kind of solar cell that is commercialized in small scale and being introduced by the PV industry into the market. This cell type has a rear dielectric passivation, usually by silicon oxide or aluminum oxide. And then to facilitate current flow, a laser is used to open up localized points or stripes, which forms region of contact by aluminum. So for this reason, this cell is called localized aluminum back surface field cell, as opposed to a conventional full area aluminum BSF cell, which, if you look at the cross section, has a more or less one-dimensional current flow. The PERC cell, or LBSF cell, has a kind of periodic 2- or 3-dimensional current flow pattern. And one can simulate this using multi-dimensional simulators like Centaurus TCAD or Quokka. Alternatively, some really clever folks have over the years derived these kind of approximate analytical expressions which describes the overall recombination current as well as series resistance in the base of the PERC cell as a result of this kind of multi-dimensional current flow. So these are equations that are so handy that we've actually built them into Gridler Pro. You can open up this calculator either by pressing on this base transport button in the menu bar, or when you're looking up the database of parameters related to base recombination, you can also open up the same calculator by pressing this rear local contact calculator. So let's open it up and see. So the calculator is divided up into two halves. On the left half, we need to enter certain numbers describing the base material. For example, wafer thickness, wafer bulk resistivity, wafer type. In this case, we're dealing with p-type material. So if we change the wafer resistivity, the base doping is automatically updated, assuming silicon material. The electron and hole mobilities are also updated. On the right half of this page, we enter in things that are related to the PERC rear metallization scheme. First, we have to specify the contact geometry, whether we are opening up the rear dielectric in stripes or at circular points. If we choose points, we also get to select whether the distribution of points is in a square kind of array or hexagonal array. Contact width or diameter refers to the size of the circular points. Contact pitch refers to the distance between the points. Point contact resistance refers to whether or not physically at the point of contact between the metal and the semiconductor, whether there exists contact resistance. Bulk lifetime refers to the carrier lifetime of the base material itself. Contact SRV. SRV stands for surface recombination velocity. It's a term used to describe the strength of recombination at the metal contact points. Rear passivation SRV describes the strength of recombination at the dielectric passivated areas on the rear. So in the last video, we've covered this Gridler database, which you can look up typical or best-in-class values for many parameters. So here as well, in this calculator, we can also look up typical values related to, for example, point contact resistance. For example, Trina Solar has reported value of 2.2 milliohms centimeters square. We hit apply and that value is transferred over to the bulk. Bulk lifetime, we look up p-type monocrystalline material. So again, we can use a value reported by Trina Solar of 360 microseconds. Contact SRV, Trina Solar has reported 333 centimeters per second. Rear passivation SRV, we can use 10 centimeters per second. So you'll notice that anytime that any of these numbers are updated, all of these parameters are then used to calculate effective parameters. The first is effective rear J01. So this sums up the recombination in the base. And then we have something called effective rear contact resistance. So this summarizes after considering the whole multi-dimensional current flow and also whether or not there's actually any physical contact resistance happening at the metal semiconductor interface. The calculator will come up with an effective series resistance to describe the series resistance as seen by the solar cell after all these effects. We could also check this box called Simulate JSC in non-shaded region. So this is just a kind of rough calculator which uses a certain simulated generation profile for a cell with either pyramidal or iso texture with an arbitrary anti-reflection coding and a certain arbitrary scattering parameters inside the base. It then calculates after consideration of the diffusion length that's produced by the numbers that you have entered, what would be a plausible short-circuit current density in the non-shaded area of the cell. So you could see, for example, if we reduce the bulk lifetime to 50 microseconds, then this JSC value drops, and this is accompanied by a rise in the effective rear J01. So here we just set it back to what it was before. So for the effective rear J01 and the effective rear contact resistance, if we click the apply button next to them, these numbers will be transferred to the relevant boxes. So effective rear J01 goes to the J01 boxes belonging to the rear plane. The effective rear contact resistance value is transferred to the box next to rear metallization finger contact resistance. We can also hit apply next to the calculated JSC, and this number is also transferred now to the Wonsan JL in the non-shaded area on the front. So that very quickly allows us to calculate plausible base recombination parameters as well as base and local contact resistance in the PERC cell, and then we can of course redo our IV curve trace and obtain updated IV parameters. So now the VOC is pretty decent for a PERC cell, although the fill factor is really poor, mainly because now suddenly we have a really large resistance introduced by this rear local contacting scheme. So let's open up our calculator again. This time we can press base transport. Maybe we decide that we want to go with stripes contact instead of point contact so that we have more contact area. We probably need to increase the pitch between the stripes a little bit. So now we trade off lower effective rear contact resistance for a slightly higher effective rear J01 as well as slightly lower JSC. So we update these values. And okay, slightly lower VOC but better fill factor and efficiency. So the fill factor continues to be a problem, but now it's mainly because we've entered quite high values of J02 in the base, as you can see. But of course that is a different story. So I hope that you see the rear local contact calculator. It's a very good tool in the design stages of a PERC cell, for example. So together with all the other features of Gridler Pro, including the sophisticated metallization pattern designer, loss analysis, which we'll cover later, and the ability to construct an efficiency improvement diagram by changing cell parameters to state-of-the-art, which we'll also cover later, that you'll find the software to be an excellent tool for the design and simulation of PERC cells.